Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Just as promised, today we will take a look at an example for each of the three cases of area between curves discussed in the previous video. Please recall, from case 1, we just had two different functions that intersect and they form an area between them. That means the x-coordinates of their points of intersection will set the boundaries for our integral, and then we take that integral from the upper function subtracted by the minor function. Or in other words, upper minus lower function. So let's take a look at an example. Let's say we're tasked with finding the area between x cubed and x squared minus x on the interval 0 to 1. Now, before we do any calculations, I would like to first visualize these two functions on the graph. X cubed would look something as such. And then x squared minus x would look something like this. And let's just say the interval is from 0 to 1. That means we need to find this area right here. In this case, a good thing is that we do not have to equate these two functions to find the points of intersection because they have already been given. We only have to evaluate the area from 0 to 1, meaning our integral is going to be from 0 to 1. Next, we have to subtract the upper function from the lower. From the graph, in this part of the area, we can clearly see that x cubed in blue is above x squared minus x on the bottom. And at this point, you should be able to evaluate this integral with ease. The antiderivative you're going to get is x to the power 4 over 4 minus x cubed over 3 and plus x squared over 2 from 0 to 1. And finally, all you have to do is plug in ones, because plugging in 0 just gives you 0. So here we have 1 over 4 minus 1 over 3 plus 1/2. And the answer is 5 over 12. To be more specific, the area would be 5 over 12 units squared. Okay, so now let's move on to the second case. Please recall that in the second case, we still have two functions, however, they form two pieces of areas. Once again, we do have to establish our bounds of the integral by equating the two functions unless the bounds are given, just like in the previous exercise. Next, we have two different options. We can either evaluate two different integrals, one with one function on top and the other integral with the other function on top, or we can just put the absolute value signs and do one function minus the other on the interval from a all the way until b. We will use the two functions x cubed plus 2x squared and x squared plus 2x as an example. Once again, I'd like to first visualize these two functions. The blue function x cubed plus 2x squared would look something like this, and the parabola x squared plus 2x is going to be something as such. Now, I did make a slight adjustment to the cubic function because it was extremely inaccurate. Here now, with the revised graph, you can see that these two functions form two parts of the area. This bigger part, and right here we also have a smaller part. Please note that this time we do not have bounds to work with which are given, which means we have to find them ourselves. So step number 1 would be to find these 3 points of intersection. That means we have to equate x cubed plus 2x squared to x squared plus 2x. I then move everything to the left-hand side and equate this to 0. And then I can actually factor out an x, which would leave x squared plus x minus 2 in the parentheses. And then once again, I can do factorization with the quadratic function. And here I would get x plus 2, x minus 1 equals to 0. So that means the 3x values here would be x equals to 0, x equals to negative 2, and x equals to positive 1. So on the graph here, we would have negative 2, 0, and positive 1. So that means now we have two different options. We can construct one integral from negative 2 all the way until 1, and then take the absolute value of x cubed plus 2x squared minus x squared plus 2x. Or if you want to calculate this by hand without a calculator or any other technology, we can actually build two different integrals. So the area here would be equal to the integral from negative 2 to 0 of the blue function minus the green function, and then we add the integral from 0 to 1 of the vice versa, the green function minus the blue function. The integrals here are actually not very difficult to compute. We first can combine the like terms and simplify the expression inside the integral, and then we can apply the power rule for integral for each of the terms. The first integral, the antiderivative function we would get is x to the fourth over 4 plus x cubed over 3 and minus x squared evaluated from negative 2 to 0. And for the second integral, the antiderivative expression is negative x4 over 4 minus x cubed over 3 and plus x squared evaluated from 0 to 1. Now for the first part, if I plug in 0, I'm just gonna get 0. So 0 minus, and then next I plug in negative 2. Here I would get 16 over 4, which is simply 4, minus 8 over 3, and minus 4. And for the second part, I first plug in 1. So I get negative 1 over 4 minus 1 over 3 and plus 1, and subtract 0, because when plugging in 0, here we just get 0. And the final answer that you should get is 37 over 12. So now we can actually move on to the last case. For case 3, please recall that we had two different functions that intersect. However, the area is now bounded by two functions and also the x-axis. And also the area is actually bounded by two different functions at two different intervals. So that means here, unfortunately, we do not have another way other than doing two integrals. As an example, we use the two functions 1 over x and x raised to the power of 2 over 3. And the area is also bounded by the x-axis and the vertical line x equals to 3. Visualizing this, we can see the two functions and the vertical line x equals to 3, and the area formed is everything that is shaded in red. However, these two functions do have a point of intersection which separates the areas, meaning that's exactly where the bounds of the integral will change. First, equating these two functions, you will get that x is equal to 1. The other bound we have is x equals to 3, and the beginning bound that we have is going to be x equals to 0. So that means for the front part of the area, specifically from 0 to 1, we're going to take the integral from 0 to 1 of our green function x raised to the power of 2 over 3. And for the second part of the area, we'll take the integral from 1 to 3 of our blue function 1 over x. Now this integral can be calculated very easily. The antiderivative expression we get here would be x raised to the power of 5 over 3 divided by 5 over 3, or in other words, 3 times this x expression over 5, evaluated from 0 until 1. And the latter integral, we would get simply ln of x evaluated from 1 to 3. Plugging in your values, you should get, for the front part, 3 over 5, and for the second part, plus ln of 3. You can leave your answer as such in exact form, or you can also use a calculator to approximate that this is 1.7. To end the video, I would actually like to show you a special case that can also occur. This special case would be called area along the x-axis, and you will see why in just a second. Let's say we have two functions, y equals to 1 minus x, and the other one, well, isn't exactly a function because it's y squared equals to x plus 1. Well, graphically, I can tell you that the blue function is just a linear function, while y squared equals to x plus 1 is going to be a laying parabola. So that means we need to find this area right here. While here, everything that happens is that x and y values would technically switch places, meaning step number 1 will be to evaluate or rearrange our function in terms of y. For y equals to 1 minus x, we can rewrite this into x is equal to 1 minus y. And for the laying parabola, we can write that x is equal to y squared minus 1. For the next step, we still need to establish the bounds of the integral, specifically where these two graphs intersect. So that means we need to equate them to each other. However, this time we'll be equating functions that are expressed in terms of y to each other. So 1 minus y equals to y squared minus 1. What we get is y squared plus y minus 2 equals to 0, and we can solve this using factorization. Y plus 2 times 1, y minus 1 equals to 0. So that means y equals to 0 or y equals to negative 2, which would become the bounds of our integral. I can tell you that you can imagine this as the function being flipped. This entire graph was flipped and then also mirrored. So that means technically we're evaluating the integral from negative 2 to 1 of the linear function subtracted by the quadratic function. And most importantly, the integral here isn't going to be dx anymore, but dy, because our variable has changed. But please do note one thing, that here it would be safe to put absolute value signs, simply because there is parts of the area that is below the x-axis, and we want to make sure we don't subtract any area out of the total one. Now, as calculus and integral experts, you can try this on your own, and the answer you should get is 9 over 2. So that's it for today. Starting from the next video, we will look at volumes and how to find them with integrals. So I hope to see you there and have a nice day. Bye!